Good morning. I'm sharing. Good morning to everyone again. This is the session before lunch. I am the chair, and we have 3 talks. I will wait 5 minutes, but if you have many questions, we can use half an hour. We just cut out the questions. Move on to the next talk, and Gregor will tell us as well.
Good morning. First, many thanks to the organizers for putting together this very nice program. So I want to tell you about a study we did more than 1 year ago in collaboration with 2 colleagues from IBM Quantum in Israel, Liran Shirizli and Hagai Landa. And I'm working at the Institut de Physique Théorique, a few kilometers from here. So when you have a quantum computer or a quantum processor, of course, what you would probably like to do is to perform some complex task with it. But we know that the current devices are quite noisy, and I think it's important to get a good quantitative understanding and good quantitative model for the different sources of noise and the different unwanted couplings that are present in this device. So that's the motivation here. Can we construct a model for the dynamics of an assembly of qubits in a superconducting quantum processor? More precisely, just the dynamics of idle qubits. I will tell in some details what I mean by that. So the first part, I will describe what is the model we propose, how we determine its microscopic parameters. And once the model is fixed, all parameters are fixed. The question is, can we use this model to understand quantitatively, to reproduce quantitatively the dynamics of a collection of qubits that we initialize in some non-trivial entangled state, a bit like in a quench. We prepare the states and then we let them evolve under the action of this noise model and various Hamiltonian terms, and we compare with the experiments. So that's the plan. I'm happy to take your questions during the presentation. So the processors that are being used in these studies, they belong to this Eagle generation from IBM Quantum. So they have 127 superconducting qubits, that the so-called transmon technology. Basically, each qubit is some anharmonic oscillator, and because it's anharmonic, we can focus on just 2 levels. So these are not the latest processors from IBM Quantum, but still relatively recent. They have a connectivity which is displayed here. It's called a heavy hexagon layout. So you have this large plaquettes with 12 qubits. Also, a remark here is the systems are quite inhomogeneous in the sense that all qubits are different. On this plot, which you can find for each quantum processor from IBM, here, the color of each circle, the color of each qubit encodes one of its physical property, which is the coherence time T1. And you see, they don't have all the same color. Some are bad qubits. They are in dark here with coherence time T1 around 30 microseconds, and some are better. The light ones, it can reach 700 of microseconds for T1.
So the connected distance for what?
So I will not really discuss the gates in this, but that's when they are connected by a bond here, it means that the processor can natively apply a gate between these 2 qubits. In case you want to apply a gate between 2 qubits which are not connected by this lattice, you need to put intermediate swap gates or things like this. So the native gates are those where when 2 qubits are connected. So Okay, so let's start. Let's construct. Let me explain what is the model we propose. A very simple one. So of course we start with just two levels of the qubit. We will ignore the higher excited state of the anharmonic oscillator. Okay, so sigma z -1 or 1 for the two logical states, and there's an energy difference. So each qubit will have its own delta A. So we are working in a rotating frame approximation. So the delta A are not really the gap of each transmon, which is in the gigahertz range. Here it's this gap minus the derived frequency. So at the end, we will have a time-independent Hamiltonian, and delta A will be the kilohertz. Okay? Because that's not enough to get a precise description of how they will evolve in time. It turns out that in these solid-state systems, it's well known that this energy difference between the 0 state and the 1 state can in fact be affected by some kind of spurious degrees of freedom, which has to do with some charge parity in the nearby electrode. And depending if this charge is even or odd, in fact, this will induce some small frequency shift. Well, sometimes not so small, which we call nu. And so this will be one parameter of the model. In fact, there will be one nu for each qubit. And this is an important ingredient to get a quantitative description of the dynamics. Unfortunately, this parity is not controlled. So during each experiment, we will assume it's constant, but from one shot to the next, from one experiment to the next, it can change randomly. One source of error that we include as an ingredient in the model. It has been known to exist at the level of a single qubit, but here we will include this in a many-body description. Okay. There's another kind of unwanted term in the Hamiltonian we need to include, which are cross terms. So of course, coupling between the qubits is something useful and needed when you want to apply gates. But it turns out that in this Eagle generation of processors from IBM, there is some residual interaction between nearby qubits. By nearby, I mean they are neighbors in this heavy hexagon geometry that cannot be switched off. So, and in the simplest approximation, it's a kind of Ising coupling between nearby qubits on the hexagonal geometry. And they are not all coupled in the same way. So this is a family of parameters we put in the model that we'll have to determine precisely to reproduce the dynamics. Okay, so far these are simple Hamiltonian terms. Now let me talk about the non-unitary part of the dynamics, the dissipation or decoherence term. So we propose the simplest master equation description in continuous time via Lindblad equation. And so in addition to the Hamiltonian terms I have discussed already, we consider the two most standard jump operators. So because these systems are operating at very low temperature, it seems like it's enough to consider the dissipative processes during which a qubit spontaneously goes from the excited state to the ground state. The reverse processes are quite rare. So in this model, we just included this one. That's one jump term. But the rate at which this occurs is potentially different from each qubit. That's something I mentioned. So there will be one G0 parameter here for each qubit that we need to determine if we want a quantitative description. And we also include dephasing. It can be viewed as an effect of some noise that kills the phase coherence between 0 and 1, and that's related to the T2 coherence. And again, each not all qubits have the same T2, so there will be one G2 parameter per qubit. Okay?
What's the order of magnitude of T2 and T1?
What's the
order of magnitude between them?
Well, typical order of magnitude is 100 of microsecond. I will show numbers
for both of them, so they are compared.
We'll see in the more or less, yes.
Is it possible that they compensate to zero?
Good question. Not sure. Well, in principle, it could happen. Okay, so these are the most standard ingredients in the model. Okay, so at this point, we have already introduced lots of parameters. How do we determine them? So the idea is we will fix them by just relatively standard 1 and 2 qubit characterization experiment. So in this big processor with 100 qubit, we just it's possible to just isolate one, perform a very simple experiment like initializing it in the one state and just monitoring the probability that it's still in one as a function of time. This one you get T1. So you do this for each qubit, and that gives the T1 of each qubit. So these are very standard calibration or characterization experiment that is doing very frequently by IBM, but we also include this in our protocol. It's also possible to determine, so with this single qubit characterization, when it's easy to extract T1, T2, also delta, and the coupling to the, I have not explained details here, but I'm skipping some detail, and also the coupling between the charge, the spurious charge parity to the qubit. So just focusing on one qubit, one can already extract its own parameters, essentially. Because each data point here, so the full lines are fits, and each data point, in order to have sufficiently small error bars, and that's important if we want to get these parameters accurately, each data point is something like 1,000 shots. Okay, and now remember that in the Hamiltonian we had some cross-term couplings, some leading interactions between nearest neighbors on the heavy hexagonal lattice. So for that, we need to isolate qubits in the processor, initialize them in some state, monitor their dynamics to extract their crosstalk coupling. Okay. So after you have, so that's a lot of fits, lots of experiments focusing on 1 and 2 qubits. But at this, once you've carried out this, all the parameters of the model are fixed. No free parameter anymore. Okay, so you were asking about numbers. So these are so here we focused on one plaquette, which was a relatively good one. And for each of the 12 qubits, you have the T1, the T2, the coupling to the spurious charge, its gap, and also the crosstalk to each neighbor. Okay. So you were asking what, so you see the T1 and T2 are roughly of the same scale. This generation.
Is it the problem that the coupling to the spurious to the parity is bigger than the gap, or?
Yeah, it's no, it's yeah, it may be a problem if you want to perform some task on the machine. Again, yeah, this charge parity is essentially constant over minutes. So but the problem is when you repeat experiment, then the charges have changed, the charges have moved from one electrode to another, and then you are. So that's why in practice, the calibration and determination of delta is done before you do anything, essentially. Okay. So then I want to, because soon I want to show you that I will compare experiments on the collection of qubits, not just 1 or 2, with simulations. So I want to say a few words about how we do the simulations. So depending if the charge associated to 1 qubit is even or odd, it will evolve according to a different Lindblad equation, because it's energy difference between 0 and 1 will be slightly different. So in principle, so when you do one experiment, you don't know if a given qubit will be coupled to an odd or an even electrode. But so it's natural to consider the mean or the average. If you do many shots, the data should correspond to this density matrix, which is a combination of what happens in the odd or even cases. So what we do, but that's a bit costly because if you have n qubits and if you want to do numerical simulations, one should do 2 to the n simulations, corresponding to all the combinations of odd and even on each electrode. So what we do instead, we add n pseudospins in our numerical treatment, and we initialize, so the pseudospins encode the parities, and we encode the state of this pseudospins in a mixed state where each one has equal probability to be even or odd. So then we just have one single Lindblad equation, but with 2 n qubits, n real ones, n logical ones, and n parities. So that's a summary of this model. We have the qubits, we have the crosstalk, this Ising interaction. Each qubit has jump operators in the Lindblad description corresponding to this T1 and T2. The couplings to the charge parities, and the charge parities are initialized in a fully mixed state with equal probability to be up or down. So that's the model. And because we carried out the characterization experiment on 1 and 2 qubits, all parameters are fixed now. So we want to simulate the model. So we'll not simulate the dynamics of 127 qubits. We will focus on one plaquette at a time. So basically 12 qubits plus the 12 parity. So we have to simulate a problem with essentially 24 spins. So as you know, the density matrix is usually a big object. If your Hilbert space has dimension d, it's a d by d matrix. If you want to solve in a brute force way the Lindblad dynamics, you have to consider the Lindblad or the Liouvillean operator that acts on this density matrix. So it's an even bigger object. So it's well known that in practice, beyond a few qubits, doing a brute force solution is not possible. And here, 24 is already too much.
Sorry, I missed. What is there a dynamics for the parities, or just the
no? But they get they don't have dynamics, but they get correlated with the qubits.
But they're like classical spins then. They stay what they are forever.
Yes. But including them allows us to, in one simulation, to get the average over all possible parity configuration. We could have, okay, even 12 qubits, it's already, I think, a lot for a brute force solution of the Lindblad problem. Okay, so what we do is we use some compressed representation of the many-body density matrix using matrix product operators. We have heard about this several times yesterday and so on. So this is a relatively standard method. It turns out that in what I'm going to show you, the states are not too correlated. So even though we are not in strictly 1D because we will simulate a plaquette, so that's a ring, it turns out that the MPO simulations are not too demanding, and with a bond dimension of a few hundred, the calculations are almost exact. Okay, for those who are interested, the code we used is open source. It's available on GitHub. For people interested in technical details, so the way we implement the time evolution, it's based on this. It's an MPO scheme that was initially introduced in the context of unitary evolution of pure state in this paper. So, but now we use it for the Liouvillean, so non-unitary evolution, and we extend it in order to have a relatively small Trotter error. So very small error in terms of discretization, scales just like tau to the 5. we choose this because it allows for a long-range interaction. So it's quite general. You can study very different geometries. You're not stuck to study just a chain of qubits. And here we are indeed not on the chain because it's a ring. So that's an advantage of this compared to maybe. Okay. And there's a Python interface with the IBM library Qiskit. Okay. So the idea is that we will use this model to study some kind of quench. We'll prepare the qubits on a plaquette of the processor in an entangled state. And then we just let them evolve and check experimental data against the model. So what is the initial state we prepare? It's a particular type of cluster state, okay? A graph state. What is the graph state? You give yourself a set of qubits connected by some edges, and the graph state is defined as follows. You initialize all the qubits in the plus state, so 0 plus 1, and then for all the edges in your graph, you apply a control Z gate. Okay, that's the definition. So it's a cluster state, so you can define stabilizers. In fact, for each qubit in your graph, you can write a stabilizer. It's a product of 1x times some Z polymatrices for the neighbors on the graph. Okay. I don't have time to really motivate why these kind of states are interesting, but we find them at several places in quantum information theory, from measurement-based computation, error correction, also. So, and it turns out that, so we consider various, some small graph state and a bigger one. It turns out also that this is not too complicated. Preparing a graph state where the graph is this is not too complicated on this processor, because it matches the connectivity of the qubits. Okay, so these are some entangled state. Well, I'm saying it's not too complicated. This is the gate sequence to prepare the graph state corresponding to this graph here. So you first need to prepare the plus state and then the control Z, but the control Z gate is not a native gate on this processor. So you have to write it in terms of the native gate. So after this, you have some good approximation of the graph state. And then we just let the qubit evolve, subject to their coupling to the charges, crosstalks, noise. And here is the result. For this particular hexagon, each plot here represents the expectation value of one of the 12 stabilizers of this graph state. So by construction, it is initially equal to 1. So all the curves start from 1 or almost 1. State preparation is not perfect. On each plot, so you have the stabilizer. I told you this is 1x and 2z. Okay, so it's an expectation value of an operator involving three qubits. As a function of time, the scale is tens of microseconds. And on each plot, you have the experimental data point. So again, each point is basically 1,000 shots to get small enough error, statistical error bars. And a continuous line, which is the result of the simulation of the model with the 12 plus 12 qubits using MPO. So I think what is quite remarkable, so this was one of the hexagons where the match was the best. What I think is quite remarkable is that, so you see that these expectation value have some rather non-trivial evolution as a function of time. And here, the agreement is sometimes very good without any adjustable parameters, because all parameters have been fixed during the 1 and 2 qubit characterization experiments beforehand. Okay, so I think this is an indication that the model is very reasonable and quite quantitatively quite accurate. Okay, and then the last slide. Of course, what we gain after doing that is that then we are confident that we have a relatively accurate representation of the qubit state in the classical computer, in the MPO simulation. So we can also address questions or look at observables that are difficult to measure. Or so I'm not going to describe these two plots in detail, but for instance, one could look at the fidelity between the initial graph state that would stay here forever if we had a perfect machine, with the state that is actually realized. And of course, so it drops as a function of time. So that's the blue line. Also, things you can do is that you can view the model as you can use it as a kind of emulator of the real device, possibly to invent or to play with some error mitigation protocols, or possibly also in the future simulate error correction or things like this, once you have a rather solid noise model, as we have here. In particular, something we did and that I've not discussed today is we also played with some dynamical decoupling, which is a way to reduce the errors by introducing additional gates, both in the simulation and in the experiment. And we see indeed some improvement. This is the mean value of the stabilizer. So it's 1 and then it decayed. Again, experimental data and simulation here. And same data and simulation, but adding what I have not discussed, which are these additional gates to mitigate the errors. And we see indeed that the stabilizer get larger values. And with this, I thank you for your attention.
Thank you. So some questions, we have quite some time.
So what is the entanglement in the...
Yeah, unfortunately, I don't have a plot, but of course, that's a question that is easy to address if you have the MPO representation of the state. Well, at least correlations, and quantum entanglement is a bit more difficult to extract when you have mixed state. I don't have a plot, but as I said, the MPO simulations are not very demanding here because the state is not extremely correlated. What I can just say is that in a...
Yeah, operator entanglement of your density matrix.
Yeah. Yes. So just to start, the von Neumann entropy of a graph state like this, for every non-trivial cut in two parts, I think it's... okay, I should not say, is it log 2 or 2 log 2? I think it's 2 log 2. And so the operator space entanglement is 4 log 2 initially, and then it only goes down.
Oh, yeah, okay, but what bond dimension you need?
It's something like 200, and then it's almost exact.
Okay, but
these are not super...
so if you had more of these...
yeah, of course, that's for 12. Of course, if we had to study bigger systems...
So it's still quite... I mean, so the quantum machine still can compete with the classical computer?
The problem... Yeah, in principle, at least in the initial... Well, it depends what initial state you prepare. I mean, if you just... yeah, here we did not attempt to prepare a state with some larger scale entanglements. We focused on, I mean, to have a very...
There's another question.
Two questions. First, so you're saying now this is sufficient, or would it be good to add more general channel, like, I don't know, then capture better the lower, or what?
Yeah, of course, yeah, it can probably be improved, but well, I think that, you know, it's already a
good starting point.
Yeah, maybe for, you know, maybe we go forward trying to simulate something more complex, maybe a larger cluster of qubits, maybe we would realize some additional values.
And second question, how does your simulation compare to the IBM simulation? Because like you can ask it to predict. Like, is yours better than their?
Well, I don't know. Well, the idea behind it is still to use the MPO and some network representation. So
yeah, no, I'm just asking because they give some sort of estimate of what to expect from the noisy. Like, do you have the feeling that these estimates are not good, not having the right?
No, I don't have a precise answer.
So I also have a question. So the am I right that when quantum computer does nothing, it simulates actually disordered average interacting localized system?
Yes.
Or again, the question is it localized, and can we learn something about many by delocalization, right? Because you have already disordered averaged it, right? Because of this ancilla spins, and there is some interesting dynamics happening still, right? So it's open, and so.
No, you're right.
But again, is there any conclusions that we can reach?
It was not the initial goal, but it's clear that we see that even idle qubits have an interesting life on their own.
But if you push it, let's say, to some crazy times, will system relax, or what is because of dissipator? It's just gonna.
Yeah, here. After a few hundred of microseconds, we are close to a trivial steady state. Yeah.
Which is
everyone in the steady state, because we don't allow for excitation, thermal excitation, so then we at the end all go to the zero state. That's the steady state of this level.
Oh, the last two questions. So
your model is completely Markovian. Do you see any non-Markovianity effects coming out, or this is?
I don't know. What I can just say that if you don't include the coupling to the charge parities, then there are indications of some non-Markovian behavior, just due to the fact that because of these charges, which parities are essentially constant over one shot, but fluctuating from one shot to another. So if you don't include this, then you have problem with a purely Markovian description.
The last.
Thank you very much. If you consider hexagon with light color, so better qubits, the model is not. Because
I think so I don't have in mind. This we have tried this on several hexagons. This is one of the best. If you go to a place where there are a few qubits with very short coherence time, you get less oscillations and
my question is that this hexagon is involved with the best qubit of the model of the computer or the
this is an hexagon where on average you have one of the best qubits on the whole processor. Yes. At least where we had the best agreement between. So it could be that on some other hexagon there's a noise term that is not in the model, and then we got a less good agreement. Because the model doesn't contain everything. At least for an hexagon like this one, it's relatively good description.
Thank you everyone for lively discussion. Thank you myself.